All right, we're finally on the last lesson of acids and bases. This is acids and bases 5. This is by far our longest section, and so make sure that you're going back and just putting concepts together, reviewing as we go. I apologize in advance for my voice. There is something going on in my throat, so I sound like a witch at times and a squeaky mouse at others, so I apologize for that. But we're going to go ahead and get started here. We're on acid and base titrations. Now we did titrations, if you'll remember, back when we were talking about redox reactions. And so we know basically what a titration is, but when we get into acids and bases, we're going to follow those titrations a little more closely and investigate them in more depth. So a titration, specifically with acids and bases, is used to determine the concentration of an unknown in a solution. What happens with a titration is you have a strong acid of a known concentration and it is added to a base, which will have likely an unknown concentration, or you'll have a strong base of known concentration added to an acid with an unknown concentration. In those mixtures, you must have what is called an indicator. And an indicator is a separate chemical that we add just a few drops of, and it is going to change colors and tell us that we have arrived at what is known as the end point. The equivalence point occurs when the same number of moles of acid and base have combined. And one of the goals when we do a titration is to set up the titration in such a way that our end point is identical or as close as we can get it to our equivalence point. And what that's going to do is cause the solution to change colors when we have equal moles of acid and base. And that will allow us then to do some stoichiometry and find our unknown concentration. So the equivalence point and the end point are not the same thing. The end point is when the color changes. The equivalence point is when the moles of acid and base are equal. But our goal is to make it so that they're the same. And we'll talk about how to set up the experiment so that occurs. Alright, so we have 3 types of titration that we'll go through. The most basic type is when we have a strong acid and a strong base. This is complicated, though, when we have a weak acid and a strong base, or a weak base and a strong acid. Of course, there's a 4th type, if you're kind of following along. The 4th type would be when we have weak acid, weak base titrations. We do not run those titrations because they are almost useless. The math is so convoluted that it really doesn't tell us much about the solution when we do that type of titration. Because remember, a weak acid is in equilibrium and a weak base is in equilibrium. But if we use a strong acid or a strong base, we're going to have reactions that go to completion, which we prefer. So these are the 3 types of titrations that we'll focus on. Alright, so let's start off with a strong acid, strong base titration. So in this example, we have 3.0 times 10 to the first power. I'm not sure why they decided to write it like that. Milliliters of 0.5 molar HCl. And we're going to titrate it with 0.5 molar NaOH. Now this is a rare example where we actually know the molarity of both of them. And also we want to identify HCl, we know that is a strong acid, and NaOH, we know that is a strong base. So anytime you're encountering a titration problem, go ahead and identify what it is that you have in the solution. So in this case, we have a strong acid and a strong base. And that's going to guide us as we go through our titration problems. So if it's strong and strong, we're going to treat the titration problem one way. If it's strong and weak, we'll treat it another way. And we won't have any weak or weak. They want us to find the initial pH of the HCl, the pH after we add some NaOH, the pH after we add some more NaOH, and even more. So in a titration, if you remember, you have it in the Erlenmeyer flask, and then you're adding it through the burette. So you're adding it a little bit at a time, right? You open that stopcock and some goes in, some goes in. So they're asking, okay, what is the pH before you let any out? What is the pH after you add 15? What is the pH after you add 30? What is the pH after you add 40? So we're just tracking as we go through the titration. To start off, we want to know what is occurring in the solution. So they have given us the net ionic equation. This is the net ionic for any strong because we have HCl, which is strong, so the chlorine is a spectator, and NaOH, which is strong, so the sodium is a spectator. So anytime you have a strong acid and a strong base, this is going to be your reaction. Alright, so if we want to find just the initial pH, no reactions occurred yet, we're just talking about the HCl that is down in the Erlenmeyer flask, we assume that if it's a strong acid that 100% of it has dissociated. So if we have a 0.5 molar solution of HCl, then we know that it is also 0.5 molar H+. So to find the pH, we simply plug in pH equals negative log of our H+, and we see that the pH at the beginning of this titration in the flask, before we've added anything from the burette, is 0.30. Okay, very, very low. We have a fairly high concentration of a strong acid. Alright, now let's see what happens after we add some of the titrant, which is our NaOH. Alright, when we do these problems, we are going to treat them as ICF problems. Okay, very similar to our ice tables or rice tables, right? But we are using the F because if we have a strong acid or a strong base involved, which we always will in a titration, then these are going to go to completion. So here's our reaction. And we're going to use an ICE or an ICF table since we have a single arrow to solve. Now, when we're doing titrations, it is important that we use moles on our ICF table. And the reason is because we're adding solution. And as we add solution, the volume is changing. Well, if the volume is changing every time you add something, then your molarity is also changing. So we don't want to use molarity on these tables because it's constantly changing. However, our moles of the stuff in the flask, right, here's our flask, it has our HCl in it. The moles of HCl is not changing. The only thing that's changing is your moles of NaOH as you add it. Okay, so for titration problems, we're using moles on our ICF table. So first off, let's find the moles of the H+ and the OH- that reacted. So if we look, we have 30 milliliters, if you look back one slide, 30 milliliters of 0.5 molar HCl. So how many moles is that? Molarity equals moles over liters. So to find moles, we need to multiply molarity times liters. So 0.5 times 0.03. So for our H+, we have 0.015 moles. Now for our OH-, we've added 15 milliliters so far, and it is also 0.5 molarity. So 0.5 times 0.015. We have 0.0075 of the OH. right? And before the reaction occurs, we have some water, but water is a liquid, right? So it is irrelevant on our ice table. All right, now we want to know how much of these are left over when we're finished. So if we look, we need to identify our limiting reactant whenever we have a single arrow. It's not an equilibrium, so we have to identify the limiting reactant. In this case, the OH is smaller than the H+, and they have the same coefficient. So that's our limiting reactant. Your limiting reactant goes to 0. We have minus X. They both have a 1. Minus X. And we don't know what this is. 0.015 minus X. Right? So we have no OH left. And we can use this to find X. 0.0075 minus X equals 0. So X must be 0.0075. So in the end, I have 0.015 minus 0.0075. 0.015 minus 0.0075 is 0.0075. It's half as much. So I have 0.0075 of my H+ left. Now what is this? This is moles, right, of my H+. Okay, so let's just pause there. We just mixed some acid with some base. And we said that the base was our limiting reactant. So if we look right here again, we ran out of the base. We made some water, but water has no effect on the pH. So the only thing we have left in the solution is our H+. So should our pH be high or low if we have only H+ left? It's an acid, right? So our pH should be low. But let's figure out what it is. How do you find pH? pH equals the negative log of your H+, right? But it is not your H+ moles, it is your H+ molarity, which is moles over liters. So we know that it's 0.0075 moles, but what about the liters? So let's think about this. We added 15 milliliters of base. What was our volume of acid? It was 30, right? So think about the titration again. If you had 30 milliliters in the flask, you added 15 milliliters. How many milliliters do you have in the flask now? 45. 0.045 liters. Right? So pH equals the negative log of the molarity. On our ICF table, we're going to have moles. But when we go to calculate pH, we've got to change that back to molarity. So 0.0075 divided by 0.045 is 0.166 or 0.167 if you're rounding. And then we do the negative log of that. And we get 0.78 as our pH. Okay, I'm running out of room here, but 0.78 would be our pH. Now remember, we just calculated the pH before, and it was lower than that. And so when we add that base, it has gone up some, but it hasn't gone up a lot because we still have only acid when the reaction is complete. All right, so here again is that ICF table. There's our initial moles. There's our change in moles. There's our final moles. Final, okay, and then our new volume. So we have our molarity, and then we calculate the pH from there. 0.77 is what they got. I got 0.78, right? Either way. So, ICF tables for titration using moles, and then going back to molarity in the end to find our pH. All right, let's do an example where we add 30 milliliters of NaOH. Now, at this point, when we calculate moles, we've got 30 milliliters of NaOH, that's 0.5 molarity. And we have 30 milliliters of our 0.5 molarity HCl that was already in there. So what do you notice about these values? If you calculate the moles from 30 milliliters and 0.5 molarity and 30 milliliters of 0.5 molarity, you are going to get the exact same moles. So think about your ICF table. You're going to have 0.015 under H plus and 0.015 under your OH. So which one's you're limiting? Well, it would turn out that you would run out of both of them, right? So if you run out of both of them, all of your H plus reacts with all of your OH minus to produce water. So you have no H plus left, you have no OH left. So this is the equivalence point. Moles of acid equals moles of base. If you have no H plus and no OH minus and all you're making is water, then your pH must be 7. And this is true at the equivalence point for all strong acid, strong base titration. Your chlorine ions, which will still be floating around in the solution, and your sodium ions, those spectators, they have nothing to do with the pH of the solution. So if you are at the equivalence point for a strong acid, strong base titration, then your pH will be 7. So there's no calculation required. And that one is simple. You just have to recognize that that's the equivalence point. All right, let's move on to when we add 45 milliliters of titrant. So again, we want to find the moles of the H plus and the moles of the OH minus. Now remember, we said that the moles of the HCl are not going to change because it's in the flask and we're not adding any more HCl. So the moles of the HCl is still 0.015 because we have 30 milliliters of it in a 0.5 molarity solution. Now let's find our moles of NaOH. We've got 45 milliliters, which is 0.045 liters. And if we multiply that by our molarity, which is 0.5 molarity, or 0.5 moles, sorry, this is sloppy, over liters, that's what molarity is, so the liters cancel, then we will get 0.045 times 0.5, that will be 0.0225 moles of our NaOH. See if they do that a little bit neater than me. There you go. They rounded it to 0.023 moles. All right, so when we're doing titration problems, we have to find moles. We cannot use molarity on our ICF tables in acids and bases. So we have moles, and we put them on our ICF table. Notice this squiggly line here. Water's a liquid, so we're not really concerned with that. Our limiting reactant here is now the H plus. We have less of it than the OH minus, and they have the same coefficient. So that's my limiting reactant. So that one's going to 0. Okay, your limiting reactant goes to 0. So if this is minus X, X must be that value. So they just go ahead and plug it in there instead of using X's. Your OH then goes to this 0.008 moles. Right? We're looking for the pH. So we need to find the concentration of this species. You cannot use moles to find pH. You have to find concentration. So let's find the concentration of the OH minus. So we know that we have 0.008 moles, but we need the liters to find the concentration. So we've got 30 milliliters, and we added 45 milliliters to it, so we have 75 milliliters. We know that we have 0.08 moles from our ice table, and we divide by our liters to get our molarity. Now this is the molarity of the OH, and we're trying to find the pH. So we're going to have to go through POH to get there. So the POH is the negative log of the OH. So for POH, we get 1.0. Now let's think about it. All our acid is gone. All we have left is base. So should our pH be high or low? If all we have left is base, our pH should be high. So this number represents our POH, which we will subtract from 14 to find our pH. So we find that our pH is 13. All right, this makes sense because all we have left is base. All right, so let's look at those results again. Here was our initial pH before anything was added. After we added 15 milliliters, our pH was still very low. When we added 30 milliliters, we reached the equivalence point. That is at 7 because we have a strong acid and a strong base. And then when we added 45, our pH was very high, up to 13. This is the common shape of a titration curve. It starts either very low or very high, and is pretty even, increasing only slightly. Then when you get close to the equivalence point, the pH is going to shoot up or down, depending on where you started, really rapidly, and then flatten out again. This sharp increase tells you that you're at the equivalence point, and the center of that sharp increase is your equivalence point. If you have strong acid, strong base, your equivalence point will be right there in the center at 7. All right, here's breaking down those characteristics just a little bit more. The change in pH is normally very small, less than 1.5 over this flat region. So very small increases. Then we get very large increases around the equivalence point, and again very small increases after the equivalence point. All right, we'll pick back up with the next example problem on the next video.